Hello everybody, my name is Lian Shen. Today I'm going to introduce a new chaotic system with multiple attractors, dynamic analysis, circuit realization, and S-box design. This slide shows the fast portrait of the system, where we can see from the projections along the X, Y, and Z that the trajectory resembles the shape of a butterfly's wings. The parameters are set as 4944 with initial conditions of 111. As we can see, the system's solution will eventually be confined to a bounding region, which means the system produces a chaotic attractor. And second is time series. This page displays a time series of the z variable under the two sets of initial conditions. One is 1.001 and one is 1.0001. Although the initial conditions are very close to each other, the difference between the two gradually amplifies over time. This demonstrates the system's sensitivity to initial conditions, which is one of the most prominent features of chaotic phenomena, commonly referred to as chaos. And third, we're going to introduce point care maps. Here have three kinds of T-spans. One is 50, and one is 500, and one is 5000. In this short time range, the system behaves in a more regular way. The points in the Poincare section are concentrated, showing stable and periodic behavior without chaotic features. And second, T-span 500. As the time range increases, the system behavior becomes less regular. The points start to spread out, indicating the beginning of chaotic behavior. This shows the system is becoming more sensitive to initial conditions. And third, T-span 5000, long time range. In a long time range, the system enters a fully chaotic state. The points in Poincare section are highly scattered, reflecting the system's unpredictability and the coexistence of multiple attractors. Summary: as T-span increases, the system transitions from regular behavior to chaotic behavior, demonstrating the high sensitivity of chaotic systems. In long time range, the system shows greater uncertainty and complex dynamic behavior. And third, bifurcation. The simulation result shows that the parameter C changes. The system dynamic behavior exhibits different attractors. As C increases, the red and blue branches gradually separate, indicating that the system's initial conditions significantly influence the final attractor. Spatially, the system transitions from a single stable state to stability than to multi-periodic and chaotic behaviors. Presenting typical bifurcation phenomena based on the simulation result, it can be observed that the system dynamic behavior is closely related to the initial condition, and the system displays a diversity of behaviors from stability to chaos as the parameter changes. And then page 5, we are going to introduce final one, Lyapunov. This simulation result demonstrates the behavior of multiple attractors in a chaotic system under different parameter conditions, and effectively reflect the system dynamic characteristics through the variation of the Lyapunov exponent. These results provide valuable insights into understanding stability of chaotic systems and their diverse dynamic behavior, offering guidance for subsequent experimental and applied research. A red curve is the largest Lyapunov exponent, usually used to represent the most unstable direction of the system. And blue curve lambda 3, this is the smallest Lyapunov exponent, usually representing the most stable direction of the system. And this is my final presentation. Thanks everybody.